Hydropower is renewable energy resource because it uses the Earth's water cycle to generate electricity. Water evaporates from the Earth's surface, forms clouds, precipitates back to Earth, and flows towards the ocean. The movement of water as it flows downstream creates kinetic energy that can be converted into electricity. On a worldwide standpoint, it is the most widely used form of renewable energy. Hydropower has been used for centuries by humans. The electricity is typically created when the water is passed over large mechanical turbines. The water pressure forces the turbines to turn. The mechanical energy created is then converted into electricity. Hydropower has now become the best source of electricity on Earth. History proves that the cost of this electricity remains constant over the year. Because of the many advantages, most of the countries now have hydropower as a source of major electricity producer. The following aspects are highlighted in this lesson. Hydroelectric power, potential of India in hydroelectric power. Hydroelectric power, a renewable resource. The present installed capacity for hydroelectric power as on September 30, 2013 is approximately 39,788.40 megawatts, which is 17.39% of total electricity generation in India. Other renewable resource includes geothermal, wave power, tidal power, wind power and solar power. Hydroelectric power plants do not use up resources to create electricity, nor do they pollute the air, land or water as other power plants may. Hydroelectric power has played an important part in the development of this nation's electric power industry. Both small and large hydroelectric power developments were instrumental in the early expansion of the electric power industry. Hydropower is an essential contributor in the national power grid because of its ability to respond quickly to rapidly varying loads or system disturbances, which base load plants with steam system powered by combustion or nuclear process cannot accommodate. Hydroelectric plants do not create air pollution. The fuel falling water is not consumed. Projects have long lives, other forms of energy generation. These favorable characteristics continue to make hydroelectric projects attractive source of electric power. Operating principles of hydroelectric power. Hydroelectric power comes from flowing water, winter and spring runoff from mountain streams and clear lakes. The movement of water as it flows downstream creates kinetic energy that can be used to turn turbines and generators that produce electricity. The capacity to produce this energy is dependent on both the available flow and the height from which it falls. The most common type of hydroelectric power plant uses a dam on a river to store water in a reservoir. Water releases from the reservoir flows through a turbine, spinning it, which in turn activates a generator to produce electricity. But hydroelectric power doesn't necessarily require a large dam. Some hydroelectric power plants just use a small canal to channel the river water through a turbine. Another type of hydroelectric power plant called a pumped storage plant can even store power. The power is sent from a power grid into the electric generators. The generators then spin the turbines backward, which causes the turbines to pump water from a river or lower reservoir to an upper reservoir, where the power is stored. To use the power, the water is released from the upper reservoir back down into the river or lower reservoir. This spins the turbines forward, activating the generators to produce electricity. A small or micro hydroelectric power system can produce enough electricity for a home, farm or ranch. Hydroelectric power generation at facilities called hydroelectric power plants. Hydropower is generated. Some power plants are located on rivers, streams and canals. But for a reliable water supply, dams are needed. Dams store water for later release for such purpose as irrigation, domestic and industrial use, and power generation. The reservoir acts much like a battery, storing water to be released as needed to generate power. To generate electricity, water must be in motion, since water is the initial source of energy. We call this hydroelectric power or hydropower for short. The dam creates a head or height from which water flows. A pipe penstock carries the water from the reservoir to the turbine. The fast moving water pushes the turbine blades something like a pinwheel in the wind. The water's force on the water turbine blades turns the rotor, the moving part of the electric generator. When coil of wire on the rotor sweep past the generator's stationary coil stator, electricity is produced. The water flowing in the river processes two types of energy: the kinetic energy due to the flow of water and potential energy due to the height of water. In hydroelectric power plants or dams, potential energy of water is utilized to generate electricity. The formula for total power that can be generated from the water in hydroelectric power plant due to its height is given by P is equals to RHG, where P is the total power that can be produced in watts. R is the flow rate of water measured in cubic meters per second. H is called height of water measured in meters. It is also head of water. It is difference in height between the source of water from where water is taken and the water's outflow where the water is used to generate electricity. It is a place near the turbines. G is the gravity constant, 9.81 meter per second square. The formula clearly shows that the total power that can be generated from the hydroelectric power plants depends on two major factors: the flow rate of water or volume of flow of water and height or head of water. More the volume of water and more the head of water, more is the power produced in hydroelectric power plant. To obtain the high head of water, the reservoir of water should as high as possible and power generation unit should be as low as possible. The maximum height of reservoir of water is fixed by natural factors like the height of river bed, the amount of water and other environmental factors. The location of the power generation unit can be adjusted as per the total amount of power that is to be generated. Usually the power generation unit is constructed at levels lower than ground level so as to get the maximum head of water. The total flow rate of water can be adjusted through the penstock as per the requirements. If more power is to be generated, more water can be allowed to flow through it. Once electricity is produced, it must be delivered to distant locations, offices, factories, etc. Dams are often in remote locations and power must be transmitted over some distance to its users. Vast network of transmission lines and facilities are used to bring electricity to us in a form we can use. All the electricity made at a power plant comes from first transformers, which raises the voltage so it can travel long distances through power lines. Voltage is the pressure that forces an electric current through a wire. At local substations, transformers reduce the voltage so electricity can be divided up and directed throughout an area. Most hydroelectric power comes from the potential energy of dammed water driving a water turbine and generator. The power extracted from the water depends on the volume and on the differences in height between the source and the water outflow. This height differences is called the head. The amount of potential energy in water is proportional to the head. To deliver water to a turbine while maintaining pressure arising from the head, a large pipe called a penstock may be cost. This method produces electricity to supply high peak demand, moving water between reservoirs. At times of low electrical demand, excess generation capacity is used to pump water into the higher reservoir. When there is higher demands, water is released back into the lower reservoir through a turbine. Pump storage schemes currently prove the most commercially important means of large-scale grid energy storage and improve the daily capacity factor of generation system. Run-of-the-river hydroelectric stations are those with comparably smaller reservoir capacities, thus makes it impossible to store water. A tidal power plant makes use of the daily rise and fall of water due to tides. Such sources are highly predictable, and if conditions permit, constructions of reservoir can also be dispatched able to generate power during high demand periods. Less common types of hydro scheme use water kinetic energy or undammed sources such as undershot water wheels. Layout of hydroelectric power plants. The major components of a hydroelectric power plant are dam, barrage, headworks, therefore power intake, head regulator and desealing chambers, etc. 2. Head race, tunnels or channels. 3. Surge shaft or surge chambers. 4. Pressure shaft or penstock. 5. Underground and surface powerhouse. 6. Tail race channel or tail race tunnel. Hydroelectric power. India has vast hydropower potential of over 84,000 megawatts. Brahmaputra, Indus and Ganges basins contributing about 80% of this total. India has harnessed only about 15% so far. Another 7% under various stages of development, and the balance 78% remains unharnessed due to many issues and barriers. As on 1st October 2013, the hydropower potential in terms of installed capacity is estimated at 1,48,701 megawatts, out of which 1,45,320 megawatts of the potential consist of hydroelectric schemes having installed capacity about 25 megawatts. It is stated that out of 1,48,701 megawatts estimated potential of hydropower in the country, 39,788 megawatts is in operation as on 1st October 2013, which consists about 27% of the estimated potential of hydropower and 17% of the total installed power capacity of the country, therefore 2,28,722 megawatts. Hydropower in India. India is blessed with enormous amount of hydroelectric potential and ranks 5th in terms of exploitable hydro potential on global scenario. As per assessment made by Central Electricity Authority, India is endowed with economically exploitable hydropower potential to the tune of 1,48,700 megawatts of installed capacity. India's hydropower system is divided into 5 major provinces, namely the Northern region, Western region, Southern region, Eastern region and Northeastern region, with each region facing separate issues, while the Eastern and Northeastern regions are power abundant. The Northern and Western regions have greater power demands. The hydropower potential is largest in any region, with 98% of it still untapped. Northern, Eastern, Western and Southern regions have 79%, 77%, 23% and 33% unexploited hydropower potential respectively. A large part of the hydroelectric projects are concentrated in northeastern states by virtue of the availability of water and required topography, but the demand for power in these areas is not significant. River basins and their power potential. In basins, the water coverage to a single point inside the basin known as a sink, which may be permanent lake, dry lake or point where surface water is lost underground. The basin includes both the streams and rivers that convey the water as well as the land surfaces from which water drains into those channels and is separated from adjacent basins by a drainage divider. The basin acts as a funnel by collecting all the water within the area covered by basin and channeling it to a single point. Each basin is separated topographically from adjacent basins by a geographical barriers such as rigid hill or mountain. Godavari Basin extends over an area of 3,12,812 square kilometer, which is about 9.5% of the total geographic area of the country. It is surrounded by Satmala Hills, the Ajanta Range and the Mahadeo Hills on the north, on the west by Western Ghats and on east and south by Eastern Ghats. The basin lies in the state of Maharashtra, Andhra Pradesh, Madhya Pradesh, Orissa and Karnataka. The total state-wise distribution of the drainage area is 3,12,812 square kilometer. The black soils, red soils, laterites and lateritic soils, alluvium, mixed soils and salines and alkaline soils are important types of soils found in this basin. About 18.93 MHA is the cultivable area in the basin, which is about 9.7% of the total cultivable area of the country. As per latest assessment, the hydroelectric power potential of the basin is 5091 megawatts at 60% load factor, and a large part of the potential yet to be harnessed. Krishna Basin extends over an area of 2,58,948 square kilometer, which is about 8% of the total geographical area of the country. It is surrounded by the Eastern Ghats on the south, east and by the Western Ghats on the west and the north. It is bounded by the range separating it from Godavari Basin. The basin lies in the state of Karnataka, Andhra Pradesh and Maharashtra. The total state-wise distribution of the drainage area is 2,58,948 square kilometer. The black soils, red soils, laterites and lateritic soils, mixed soils, alluvium soils are the important types of soils found in this basin. About 20.3 MHA is cultivable area in this basin, which is about 9.7% of the total cultivable area of the country at 60% load factor. As per the latest assessment, the hydroelectric potential of the basin is 2997 megawatts at 60% load factor. Brahmaputra Basin. This basin extends over an area of 58,000 square kilometer, lies in Tibet, China, Bhutan, India, Bangladesh. It is surrounded by the Himalayas on the north, on the east by the Patkeri range of hills running Assam-Burma border, by the Assam range of hills on the south, on the west by the Himalayas and the ridges separating it from Ganga sub-basin. This basin lies in the state of Arunachal Pradesh, Assam, Meghalaya, Nagaland, Sikkim and the West Bengal. The drainage area lying in India is 1,94,413, which is about 5.9% of the total geographical area of the country. The type of soil found in this sub-basin is a red loamy soil and alluvial soil, sandy, clayey soils and laterite soils. About 12.15 MHA is the cultivable area of the sub-basin, which is about 6.2% of the total cultivable area of the country. This sub-basin has an abundant hydropower potential. As per the latest assessment, the hydropower potential of the sub-basin is 31,012 megawatts at 60% load factor, which is almost 37% of the country's hydropower potential. Narmada Basin. The 3% of the total geographical of the country is covered by the Narmada Basin, which has an area of 98,796 square kilometer. It is surrounded by the Vindhyas on the north, the Maikala range on the east, Satpura on the south and by the Arabian Sea on the west. The basin lies in the state of Madhya Pradesh, Gujarat and Maharashtra. The black soils are predominant in the basin. About 5.9 MHA is the cultivable area of the basin, which is 3% of the total cultivable area of the basin. The hydroelectric power potential of the basin is 1,321 MW at 60% load factor as per latest assessment. The area covered by the Mahanadi Basin is 1,41,589 square kilometer. so nearly 4.3% of total geographical area of the country. It is bounded by the central India hills on the north, on the south and the east by the Eastern Ghats, and on the west by Maikala range. The state which comes under this basin is Madhya Pradesh, Orissa, Bihar and Maharashtra. The types of soil found in this basin are red and yellow soils, mixed red and black soils, laterite soils and dacite soils. About 7.99 MHA is the cultivable area of this basin, which is about 4% of the total cultivable area of the country. The hydropower potential of the basin is 627 megawatts at 60% load factor. Hydropower development issues. The slow development of hydropower in India can be attributed to many factors, and these factors are discussed in the following sessions. Environmental issues. Afforestation and rehabilitation are the main problems linked with hydropower projects requiring rehabilitation and resettlement. Measures for project affected people. Environmental impacts therefore should be probably assessed and addressed, keeping in view needs of the people to avoid delays in execution of project. Environmental impact assessment studies and plan to mitigate the same should be carried out. Mechanism of compensatory afforestation should be planned for quicker clearance of the project. Compensatory measures for project affected people should be also planned as per guidelines to expedite project clearance. Land acquisition. Hydro projects generally suffer delays due to the land acquisition problems. Landowners often demand employment and heavy compensation in some of the power stations. The major Indian rivers are generally in strait involving more than one state, requiring concurrence of all the involved states for taking up hydro projects. In number of projects, although the same could be resolved through mutual cooperation and intervention of specialized agencies, a number of hydropower projects are still languishing due to interstate disputes. Vast hydro potential of the country is available in the areas affected by insurgency and militant problems. The law and order problem in such areas lead to delay in execution of the project as well as cost overruns. Executing agencies face security problems, resulting delays in execution of the project due to difficulties in arranging manpower deployment. Throughout geotechnical investigations at the time of preparation of DPR are required to avoid time and cost overruns. However, due to site constraints and prohibitive cost involved, it becomes sometimes difficult to carry out through investigations, resulting in geological surprises during execution of the project, leading to delays in commissions of the project. 6. Funds constraints. Fund constraints is the most important factor leading to delays in execution of projects in a number of states. Projects take up without tie-up of resources from concept to commissioning suffer from such constraints. 7. Natural calamities. As hydro projects are located in hilly terrains, landslides, hill slopes, collapses, road blocks, etc., particularly during monsoon season, because of heavy rains and unpreceded floods cause severe setbacks in constructions, leading to time and most overruns.